Today, we will be looking at the motor and generator effect, which are two key concepts in electromagnetism. They describe the relationship between electric current and physical motion. By the end of this video, you should understand how, when we use electric current to create physical motion, we refer to that as the motor effect, and when we use physical motion to create electric current, we refer to that as the generator effect. We're going to start by looking at the motor effect in more detail. Here are the key steps that you will need to understand. We begin with a coil, shown here in green, that is connected to a power supply, making a complete circuit. At GCSE physics, we assume that current flows from the positive terminal to the negative terminal in a conventional direction, as shown here by the blue arrows. Because there is current flowing through a conductor, a magnetic field is created, as described in step 2. If this point is confusing, remember that when you have a straight current-carrying conductor, a circular magnetic field is created around it. Here, that circular field exists all along the coil, but for clarity, I'm only going to draw it at a few points. I will label this the coil's magnetic field. In the next step, we introduce an external magnetic field. This is typically created by placing permanent magnets on either side of the coil, shown here by the large north and south poles in pink. This external magnetic field runs straight through the coil, going from north to south. There are now two magnetic fields, that of the coil and that of the external magnet. As stated in the fourth step, the resultant force between the two fields interacting with each other causes the coil to move. This movement is typically a turning motion in a clockwise or anti-clockwise direction. There's quite a lot going on there, so let's recap. There is a coil with a current flowing through it, as the coil is in a complete circuit. That current creates a magnetic field all around the coil, as shown here. The coil's magnetic field is opposed by an external magnetic field going from the north to the south pole of these external bar magnets. The interaction between these two magnetic fields creates force, and this force causes the coil to rotate. To determine the direction of rotation, we can use Fleming's left-hand rule to determine the direction of force on either side of the coil. In this case, there is an upward force on the right-hand side and a downward force on the left-hand side of the coil. Here, that is going to produce an anti-clockwise rotation. To summarize, in the motor effect, we are using electric current from the power supply to create physical rotation of the coil. We are now going to move on to the generator effect, where the reverse happens, and we use physical motion to create an electric current. We will begin by drawing a coil in an external magnetic field. The coil is a conductor, and when a conductor is moved through a magnetic field, cutting through field lines, a potential difference is created across the conductor. In this case, that means that as the coil is rotated around, its sides cut through the magnetic field lines of the external magnet, and this induces a potential difference across its terminals. Depending on the speed of rotation, this might be 10 volts, for instance. So far, I haven't mentioned current yet and only talked about potential difference because the coil isn't part of a complete circuit. Its terminals aren't connected. In order to allow current to flow, we need to connect these terminals, possibly by attaching a bulb to split rings as shown here. Don't worry too much about the function of the split rings just yet. We'll mention that later on in the video. For now, let's do a recap of the generator effect. We've got a coil being physically rotated and its sides cut through magnetic field lines. As they cut through, a potential difference is induced across the coil, and if the coil is part of a complete circuit, a current is induced as well. Induced is a synonym for cause or create, and we use it to talk about a current or potential difference that's being created when a coil rotates through an external magnetic field, as described by the generator effect. Try to use it in your answers, as it's a term that's mentioned in mark schemes quite often. Let's now move on to a practice question. Here, an electromagnetic lock is being used to secure a door. Before attempting the main problem about sequencing these points, it's a good idea to decide if the motor or generator effect is more relevant. If you would like to attempt this problem yourself, please pause the video now. Okay. When choosing between the two effects, look for the presence of a power supply. When a current is used to generate physical motion, that indicates that the motor effect is in action. When the switch is closed, a current can flow through the complete circuit. This current then passes through the solenoid and generates a magnetic field. This is similar to how, in a straight current-carrying conductor, a circular magnetic field is created around it. The magnetic field of the solenoid is going to act to attract this iron bolt, causing it to move. This then makes the door unlock. That was a fairly straightforward problem. Let's move on to something more difficult. In this 5-mark question, a simple electric motor is shown, and we've been asked why the coil rotates continuously when a current flows through it. If you would like to attempt this problem yourself, please pause the video now. And if you would like further help, here is a writing frame that you can fill in with words in this box. Okay, this question is about the motor effect, which should be obvious from the first line stating that the diagram is that of a simple electric motor. If this hadn't been mentioned, you could determine that it was a motor and not a generator from the presence of a power supply, providing a current to the circuit in order to generate physical motion in the form of the rotating coil. Let's start with step 1. As the current flows through the coil, going around in a loop, it creates a magnetic field. This magnetic field then interacts with the permanent magnet, creating a pair of forces. Remember how the magnetic field created around the coil is going to interact with the permanent magnetic field caused by the external magnet, creating a force on either side of the coil. I'm going to indicate this force using purple arrows acting on either side of this green coil. If I were to draw a 2D version of this diagram, it would look like this. It should hopefully be clear that these forces generate a turning effect, also known as a moment. This turning effect rotates the coil in an anti-clockwise direction about the axle. That gets us all the way to step 3. To recap, we had a magnetic field created around the coil due to the current flowing through it. The magnetic field interacted with the permanent magnet in order to create this pair of forces that then acted to rotate the coil. However, there is a problem with this rotating coil, and to understand it, we are going to use this 2D diagram. For now, I'm going to color code the left-hand side red and the right-hand side blue so that we can distinguish them as the coil makes rotations. Let's use a zoomed-in diagram. At the moment, force acts downward on the left-hand red side and upward on the right-hand blue side. If we imagine these forces acting to create a turning effect, we will get a rotation in the anti-clockwise direction. After half a rotation, the sides of this coil will have swapped, producing something like this. However, if the direction of current around each side of the coil hasn't changed, the direction of force won't have changed either. On the blue side, force will still be acting upward, and on the red side, force will still be acting downward. The turning effect of these forces is going to be in a clockwise direction. You might be able to see what happens here. After half a rotation, the forces act to reverse the initial motion of the coil, returning it to its original state. Effectively, we just get a series of half rotations, never completing a full turn. This is obviously a problem, as most motors are only useful if they can make full cycles. We solved this issue of half rotations by introducing the split ring commutator. These C-shaped pieces of metal act to reverse the direction of current through the coil every half rotation. By reversing the direction of current from, for instance, clockwise to anti-clockwise, we effectively flip the direction of force on each side every half rotation, allowing the coil to rotate smoothly. To repeat that point, by reversing the direction of current, instead of having force maintain a constant direction on the red and blue side, after half a rotation, force flips as well, meaning that it now points downward on the blue side and upward on the red side. The constant reversal of current every half rotation allows forces to flip appropriately, meaning the coil can now make full, continuous rotations instead of simply repeated half rotations. If you're curious about why force acts in this direction, you can use Fleming's left-hand rule to work it out. For instance, if we assume that on the right-hand side of this coil, current is moving in this direction, and knowing that the permanent magnetic field acts in this direction from north to south, we can use the left-hand rule to show that on the right-hand side of the coil, force needs to act upward. We can summarize our points about the split ring commutator in the final line of our answer. Each half turn, the split ring commutator reverses the current. This keeps the forces acting in the same direction, allowing the coil to rotate continuously. Now that we've looked at electric motors, let's take a look at electric generators instead. Here we have a diagram of an alternator, which is a type of generator that generates an AC current, that's alternating current. The questions asked us to explain why an alternating current is induced in the coil when the handle of the alternator is turned, making the coil rotate physically. If you would like to attempt this problem on your own, please pause the video now. And if you would like further help, here is a writing frame that you can fill in with words from this box. This time, words can be used more than once. Okay, we will start by describing the motion of the coil as it is rotated through the permanent magnetic field. I will draw the field lines of that permanent magnet just for clarity, cutting straight through the coil from north to south, and filling in the first set of blanks. The coil moves through the magnetic field, cutting field lines. When we say cutting lines, we simply mean that one side of the coil has rotated through these pink magnetic field lines, effectively cutting them. Next, as described by the generator effect, when a conductor cuts through field lines, a potential difference is induced across the coil. Remember that the word induced means create. Next, because the circuit is complete, we can see that its terminals are connected to a transformer. A current is induced as well. So, to recap the first 3 points, we have the coil being manually rotated and cutting through magnetic field lines from the external permanent magnet. A potential difference is induced. Depending on the speed of rotation, this might be 10 volts or 8 volts, for instance. And because this circuit is complete, a current can flow through the circuit, which is why we can say a current has been induced as well. Moving on to the next point, each half turn, the induced potential difference reverses direction. This means that every half rotation, the terminals flip from plus minus to minus plus. This means that in a complete circuit, current will change direction as well. If you are curious about why this happens, it's because the direction of current and potential difference is determined by the relative motion of a conductor through the magnetic field. For instance, this right-hand side might be moving upward over here, but after a half rotation, it would be moving downward instead through the field lines, therefore reversing the direction of current. You're not expected to know that for your exam, but you are expected to know that this continuous flipping of potential difference and current creates an alternating current. Just a reminder that an alternating current means that as time goes on, current flips between traveling in the positive and negative directions, effectively reversing its direction of travel every half rotation. If you were asked to mark a full rotation on this diagram over here, you would be going for what looks like a full wavelength. This pattern of alternating current is only possible because of the slip rings. Seen here, you should notice how they provide a continuous point of contact between the coil and the terminals of the circuit. If we were to swap the slip rings with split rings instead, like the kind that we saw in the last question about a motor that look like this, we wouldn't get an alternating current, but instead we'd get a direct current. Seen on the graph, it would appear that current would only go in the positive direction, taking this looping pattern instead. Keep in mind that for a direct current generated with split rings instead of slip rings, one rotation has 2 of these upward half wavelengths. However, in this question in particular, we are generating an alternating current with slip rings, so we are going to fill that into this blank over here. You might wonder if there's an easy way of differentiating this generator from a very similar looking motor, and the key is to look for a power supply, or in this instance, the lack of a power supply. Here, current is being fed into the transformer instead of being drawn from a battery into the coil. Because we are turning the coil physically and using motion to create an electric current, this is a generator, not a motor. To summarize what we have discussed so far, we can say that in the motor effect, a magnetic field is created when an electric current flows through a conductor. You should start your answers about the motor effect by talking about the magnetic field that's created. Meanwhile, in the generator effect, we can say that an electric current or potential difference is induced when a conductor cuts through magnetic field lines. You should start answers about the generator effect by talking about magnetic field lines being cut, often by a rotating coil. Here are the two processes summarized, and you may have noticed the images of a loudspeaker and a microphone next to the titles. These are two classic devices that are often examined when discussing these two effects. With a loudspeaker, we are providing an electric current to the device in order to create motion, specifically the motion of air particles, which we hear as sound. Meanwhile, with the generator effect, we are using motion, the motion of air from our voice, to vibrate a diaphragm to generate electric signals that then can be passed on to a computer or an amplifier. Let's take a look at these two devices in more detail now. When using a microphone, your voice causes air particles to move back and forth, making them vibrate. These vibrations are sound waves, which cause a diaphragm in the microphone, as seen over here, to move back and forth, which in turn moves a coil back and forth as well. The moving coil cuts through the field lines of a permanent magnet, seen here with its south and north poles, and this induces a potential difference and an electric current. Let's think about words that you can use in your answer. Instead of saying motion, we might say vibration, since we're referring to air particles vibrating back and forth. And instead of saying create, when referring to the production of electric currents, we might say induce instead. In loudspeakers, an electric current is passed into a coil that's located inside a permanent magnetic field. As the current flows through the coil, it generates a magnetic field around the coil, which interacts with that of the permanent magnet, creating force, causing the speaker cone to move back and forth, making the air particles vibrate, which creates sound waves. That was quite a lot of information delivered very quickly. Let's break it down into more manageable chunks. Here we have a loudspeaker, and a question has asked us why the cone vibrates when an alternating current flows through the coil. If you would like to try this question on your own, please pause the video now. Right, we will start our answer by talking about the alternating current that is flowing through the coil. When the current passes through the coil, it creates a magnetic field. Remember that when discussing loudspeakers, we are dealing with the motor effects, as also evidenced by the power supply that is providing a current in order to create movement. After you have described the production of a magnetic field around a coil, you need to talk about how that magnetic field interacts with that of the permanent magnet. In the next step, we state that the coil experiences a force because its magnetic field interacts with the permanent magnet's field. At this point in our answer, we need to mention how the magnitude and direction of movement can be changed in order to produce different kinds of sounds. Varying the size of the current changes the size of the force, and changing the direction of current changes the direction of force. And of course, when you modify the force, you will change the direction of movement. We are going to explicitly state this in our final step. With an alternating current, direction is constantly changing, making the cone vibrate due to the changing force. Hopefully that wasn't too bad. You can see the key concepts from the simple motor brought over to the loudspeaker, where we have talked about the interaction between the magnetic field around a coil and that of the permanent magnet. The new points are about how we vary the size of movement in order to create different types of sounds. Let's look at a more extended question, this time involving a microphone. If you would like to try this on your own, please pause the video now. Okay, the first question asks us for the function of a microphone. It helps here to think about whether we are using the motor or generator effect. Since we are using movement to create electrical signals that are passed to a circuit, we are using the generator effect. I will add that label up top over here. We are then going to describe the generator effect when talking about the function of a microphone by saying that a microphone converts sound waves into electrical signals. If this question carried 2 marks, I would go on to say it did this conversion via the generator effect. However, this is explicitly asked in part B, where it says state the name of the effect used by the microphone, so we can just include that point here. Next, we've been asked to explain how a moving coil microphone works. This is the kind of question that often carries 5 or 6 marks, and we will start our answer by talking about what happens when sound waves hit the microphone. You might be tempted to say that sound waves make the coil vibrate back and forth, but there is an intermediate step involving the diaphragm. Sound waves first cause the diaphragm to move back and forth. The moving diaphragm is then what causes the coil to vibrate. As the coil vibrates back and forth, it cuts through the magnetic field lines of the permanent magnet shown here. I will draw its field lines going from north to south so you can visualize the coil cutting through them. Writing our answer here, the coil moves through the magnetic field, cutting field lines. You should remember that when a conductor cuts through a magnetic field, a potential difference and current is then induced. The current is only induced in a complete circuit, and we need to make this clear in our answer. First, we talk about a potential difference being induced across the coil. Only then do we refer to the current that's induced if the circuit is complete. You should spot the similarities in this answer to our response about the alternator earlier on. The new points are about the diaphragm moving, which is triggered by sound waves hitting the microphone. Let's try one final question about a loudspeaker. If you would like to attempt this question on your own, please pause the video now. Okay. The question doesn't explicitly state that the loudspeaker is connected to a power supply, and instead it just mentions an electric circuit. Therefore, to name the effect used by the loudspeaker, you need to remember that a loudspeaker relies on the motor effect in order to produce motion from an electric current. When describing the function of a loudspeaker, we are going to include the definition of the motor effect, which is to convert electric signals, and in brackets here, we can say variations in current, into sound waves. This is a 1-mark question, but if we were to extend our answer, we could say that the electric signals were converted into sound waves by moving the paper cone, making the link between electric current and movement extra clear. Finally, to explain how the loudspeaker works, we begin by talking about the current flowing through the coil, creating a magnetic field. The next step is to discuss the interaction between this magnetic field and that of the permanent magnet around it. Next, we will talk about how different amplitudes of sounds are made. By varying the size of the current, we change the size of the force, making the cone vibrate. In this particular question, we've also been asked to refer specifically to sound waves, so it's worth finishing our answer by discussing how sound waves are made explicitly. The vibrating cone causes the compression and rarefaction of nearby air particles. And the movement of air particles produces the pressure variation needed for a sound wave. That is everything for today. I hope the video has been helpful, and I will leave you on the summary page of the motor and generator effect. If you are looking for more questions to do, I would recommend attempting the 2023 Paper 2, where there are 3 interesting questions on electromagnetism in general. Best of luck for your exam. I hope it goes well.